So in the last part of this lecture, we'll look at the remaining proof rules, so skip, sequencing, conditionals, and loops. So of these, the skip and sequencing ones are fairly simple, but things get more complicated when we're dealing with conditionals and loops. In particular, loops are tricky because we need to say something about the repeated behavior of some piece of code rather than just executing it once. Okay, so skip, as you might expect, is pretty trivial. So we have a rule that basically says if something holds before skip, then it also holds after skip, because skip doesn't do anything. So this is a very simple rule, and we can prove it very easily so that it just to make sure that it's actually a valid rule. It basically follows directly from the definition of what skip means to execute, because it doesn't change the state at all. So sequencing is the semicolon operator like this. So essentially this is a transitivity rule. So if we have two commands that are sequenced and we're interested in establishing that if P holds before the sequence, then R holds afterwards, then what we need to do is find some other assertion Q that sort of holds in the middle between the execution of C1 and the execution of C2. So we need to establish the triple P C1Q and the triple Q C2R. Okay, and this is a case where we have to somehow come up with that Q, right? It's not going to be particularly obvious necessarily each time. So this proof, again, is pretty simple because it's basically just using the assumptions to work backwards in a transitivity kind of sense. It's not really a terribly interesting proof either. The note that they make here is that they give the second, if you like, the second triple first, because naturally you're sort of thinking about mostly reasoning backwards in these sorts of things. So you're going from R to Q and then from Q to R, which gives you the whole thing. So it's sort of natural to think of it in that order, I guess. And in the decorated version of the proof here, they're pointing out that when you sort of apply this rule, you're starting out with P, which is this, for this little sample, is A is equal to N, and R, which is this X, is equal to N, and you've got the sequence A assigned to X and then skip. You can write the proof down by putting the Q part in the middle. Right? So if you're doing this sort of on pencil and paper, in pencil and paper mode, this is how you would do it, is sort of leave space between each of the statements and sort of fill in the intermediate ones as you work backwards, basically. Or work forwards, depending on what you're doing. So here's an example, basically, of proving that theorem up here. So you can see that the encoding of the assertions is as you would expect, and then the program is the skip thing. So the proof is basically proceeding by, like one, is this is our starting position, basically. So we've got a sequence here, so the natural thing to do is to apply the sequencing rule to split the sequencing part, and remember, if we apply it with just apply, we've got to tell the system what the Q should be, what the intermediate assertion should be. Whereas if we use apply, we get an existential variable for it that has to go before the skip and after the assignment. Okay. Now, if we think about this first case, the obvious thing that's going to be Q here is exactly this assertion that's after the skip, because skip doesn't do anything. So when we apply whole skip here, you'll see that the existential is now gone and it's been instantiated with the predicate that's at the end, or the assertion that's at the end. So basically we're going to say that Q is, the existential Q is equal to this assertion here, that X is equal to N. And in the second goal, you'll see that what was previously a use of the existential is now that assertion. So this is as we saw before, so that's why E apply is quite useful in this case. Now, here we have the same sort of problem as we had before, where if we try and apply the Hoare assign rule in this situation, because we have an assignment and we have a predicate here, we'll get a thing that's got the substitution going on in it. So the easiest way to approach it is here is to use the pre-rule again with the E apply. So now we've got now we're basically going to find a predicate, an assertion to go in this P position here, which is implied by the precondition that we actually have. So when we apply the Hoare assign, it's going to give us the substitution version, which is this second part, and then we just have to prove that these are the first one implies the second one, okay, which is straightforward as well, because they're basically trivially equivalent, and so that proves that this sequence does satisfy this triple. So this is sort of generally how you go about proving these sorts of things. You can have a look at this other example here if you like. You'll need to look at swap exercise, because that's the second homework exercise. So what you have to do in this particular case is, if you've got an assertion that X is less than or equal to Y in the precondition, and you want Y less than or equal to X in the postcondition, one way to do that is to swap the two values around. Okay, so I'm sure you've come across code in programming sense where you take two variables and you want to basically swap their values around. So you can do that with a temporary variable, whatever. So what you've got to do in this exercise is write a program that does swapping, and then show that that program satisfies this triple as the right behavior, basically. Okay. It's probably clear, I think, that there are ways to satisfy this triple in other ways. So for example, if you just set Y to 0, for example, then this would trivially be true because 0 is less than or equal to every other number. Okay, but the point of the exercise is not to just satisfy the postcondition, but actually to write a program that swaps the values around. So this, in some sense, this condition, this assertion is not as tight as we want it to be, but just make sure you write an actual swap program, not another program. Okay, so that's skip and sequencing. What about conditionals? So we can sort of approach conditionals in a similar sort of way to the other ones by this sort of rule here. So we've got a conditional here, and we've got a precondition P and a postcondition Q, and we want to be able to prove this. So how would we go about it? Well, one way is to say, well, if we can show that the triple PC1Q and the triple PC2Q, then it must be the case that this bottom triple holds, because we know that when we execute a conditional, it's going to execute either the then or the else command. Okay, so this rule here would actually be reasonable, it's valid and so on, but it's not as powerful as you might want, because it essentially throws away the information that you know about the branch that's been taken. So we actually know that if C1 is the one that's chosen, we know that B, the Boolean condition, must be true. Right? Similarly, if we know C2, if we're taking the C2 branch, we know that B must be false. And it may be the case that to prove something about, to establish the Q in the two cases, we actually need to know that information. It's not just enough to know, not just enough information to know that P holds. We need to know whether B holds or not as well. So this example here shows that. So the postcondition here is that x is less than or equal to y, and the precondition is true, right? So from true, and then say y becomes 2, we don't know anything about x. We can't show that x is less than or equal to 2 because we don't know anything, we just know true. So what we need to know is that if we take the y becomes 2 branch, we know x is 0, which implies that x is less than or equal to y. If we take the then branch, if we take the else branch, we know x is not equal to 0, and we also know that we're doing this assignment y is x plus 1, which also implies that x is less than or equal to y. So the proof rule we actually want has to take into account, well, ideally has to be strong enough to give us the information about the condition as well as the branch, the actual branch that's taken. So here's the improved version, the Hoare if rule. So the bottom is the same, but you see the top has changed. So now when we're proving the sub-goals for this rule, for C1, we actually are allowed to assume that P and B is true. This is sort of abusing the notations a little bit, but P is an assertion and B is a Boolean expression, but you get the idea informally, hopefully. So this is basically saying to prove that this first triple holds, we can assume that B is true as well as P holding. And then when C runs, we need to establish that Q holds. And in the other case, we can assume that not B holds as well. Okay, so this gives us quite a bit more power. So there's a bunch of machinery that we need. Because B here is a bit of program, it's not an assertion. We can't really combine it with another assertion very easily, so we have to do a bit of work to make that happen. So in this case, this is what this B assign BS thing is doing. It's basically saying if B is a Boolean expression, I can turn it into an assertion by basically making an assertion where the predicate that we're checking is that B evaluates to true. Okay, so we're essentially, as I say up here, I think we're lifting the Boolean expression into being an assertion. Okay, and so there's a few lemmas here that we can use. So for example, if we know, this is pretty trivial, if we know that B evaluates to true, then we know that this assertion holds in this state. Similarly, if we know it evaluates to false in this state, then we know not the assertion. And then we can formalize the if rule here. So it's a bit messy, but you can see that this is the P and B part. This is the P and not B part with the lifting inserted. And the proof is pretty straightforward using these lemmas, so I won't go through the detail of that. Okay, so there's a bunch of examples here that you can look at. I'll go through this if example, and one of the other ones, if minus plus, just down here is homework. So if we get to this position, formatting is not ideal, but you can see that the program that we're talking about here is an if with the pre and post conditions as we think. So the obvious thing to do here is to apply the if proof rule, and then we get two cases. We get one for if the Boolean expression holds and is true, and one for if it's false. So this is the then case. So you can see that we've got in the pre, this is P, and this is B holds, B is true, and this is Q in the raw. Okay, so now we've got an assignment. So we can do similar things to what we did before, which is say, well, we want to apply or assign, but we're going to use the pre-rule to make it easier, a bit easier with the wildcard. So we get to this position. So this has made some simplification of the assignment. So now we're left with the situation where we've got to show that this state here implies the state here. So notice that the state afterwards says it's x is less than y, but we're substituting in y is 2 because that's the effect of the then branch. So this is going to turn into stx is less than or equal to 2. And from this fact up here, we know that x must be 0, right? Because the condition of the if statement was true. The condition of the if statement is here, which is copied across into this position. So we can use the fact that x is 0 to turn this into 0 is less than or equal to 2, and so on. So the proof uses the standard sort of approaches that we've had before to do that. And the other case is sort of the opposite of that. So in this case, we don't really need the fact that x is not equal to 0, because we know that once we've done the assignment part, over here, we're basically going to try and prove that x here is less than x plus 1 once this is substituted in, and that's always true for any natural number, so that's easy to prove. Okay, once you've unfolded everything. So hopefully that gives you an idea of, basically we're just splitting the cases and dealing with the two branches independently and relying on the fact that we know whether the condition was true or false. We don't always have to rely on that, but the point of having an if usually is to establish some condition that you then rely on in the branch that you're talking about. And this lets you use that in the proof rule. Okay, so if minus plus is the homework. Okay, so there's a longish exercise here on one-sided conditionals. So if thens without else's, so it sort of just extends the language to have that construct here, if one, and then sort of goes along and adds all the rest of the machinery for that. So I'll skip over that because we want to get to the loops. Okay, so when we're doing loops, we want to sort of do the same kind of reasoning as we did with ifs, where we've got two possibilities for what might happen. So one is that we get to a loop and the condition is false to start with, which means the loop never executes. And that means we're in a situation like this, where we've got a precondition B is false, so we still have the precondition holding after the loop, because the loop doesn't do anything. So this is essentially, as we saw in the equiv chapter, this loop where B is equivalent to false is just the same as skip. So we get this degenerates to a skip rule, basically. But there's something else we know about this, which is that when we get to the end of this process, if B is false, we know that it's false. And it might be that that's useful for some further proof step, right? So one way of putting that is that you're never going to get to the end of a while loop unless the condition is false. So you can strengthen this postcondition by allowing that fact to be there as well, which means that afterwards it might be useful to use the fact that B is false in that in the following proof steps, basically. Okay, so that's one possibility. So the next one is you can sort of think, well, if we're not going to enter the loop, that's one possibility. What if we do enter the loop? Well, one way of thinking of that is that you have to execute the body with the P being true, and then to sort of re-establish the conditions, if you like, for reasoning about the next iteration of the loop, if there is one, then we want to re-establish P. Right, so that's what this is saying. And this is sometimes called an invariant of a loop, right? Because the predicate or the assertion P is maintained by the loop. It's not changed. But for similar reasons to what we had before, for the if conditionals, this is actually weaker than we want, because we know that if we get into the loop and we execute the command in the loop, we know that B must be true. And it might be that to prove things about C, we need to know that B was true. So we get a slightly stronger premise here, which is that we need to show that if P holds and B holds, then C establishes P again. Okay, and just as for the previous case, we by the end we definitely know that not B holds. Okay, so this rule kind of looks complicated, but it's not too bad. The main issue, to be frank with loops, is that finding the appropriate invariant is the hard part. And so lots of research has been done over the years of sort of trying to automatically work out what the right proposition P would be to be the right invariant, so that you can prove that it's maintained by the loop and so on and so forth. And if you look at other proof languages, you'll find that sometimes they require the developer to write the invariant from scratch, or they might have some automated techniques for assisting with coming up with the invariant. But that's usually the hard part about whole logic, is coming up with loop invariants. Okay, so this is the while proof rule, if you like. At least this version of it. So this is the premise, right? Just encoding what's up here. Again, we have to turn the B expression into an assertion, and then this is the conclusion, which is the thing we care about, that P beforehand, we end up with P afterwards, and the Boolean condition is false. I'm not going to go through the proof. It's a standard one for all the things, same reasons as what we've been doing before. They use a bit of automation here because we're basically doing induction on the stepping function, if you like, of the statement, which in this case is a loop. So all the other cases are dealt with by this one because they don't apply. So we only end up with a rule for while end and while loop, which are the two evaluation rules that work with while loops. So we have to consider each of those cases separately. Okay, but the important part here is the understanding of what this loop rule does. Let's see. So I think the rest of this is examples and things, and some discussion about loop invariants and things like that. So let's just have a look at an example. So in this case, we've got this program here, which is that while x is less or equal to 2, we add 1 to x, right? So we keep going until x is greater than 2, but we also start out with the assumption that x is less than or equal to 3. Okay, because if it wasn't, this would turn into an infinite loop. And we can show that this establishes x to be exactly 3, because that's the, if we start out less than or equal to 3 and just keep adding 1s until we get to greater than 2, then we're going to stop at 3. And the proof is very similar to the ones that we've seen before, where we're using the consequence rules with the apply to sort of simplify using the other rules. And then we've got a bit of bookkeeping at the end to show that various assertions imply other assertions. And these proofs are quite similar to the ones that you've been doing all the way along. Okay, so just in the beginning we looked at a few Hall triples that may have been a bit confusing in the sense that they maybe didn't make a lot of sense. So this is one of them, which is if we have this loop in here, which is an infinite loop, it turns out that this triple always holds for any p and any q. Right? So it seems wrong to say that if you start out with anything and you run this, you end up with anything you like. But it makes sense when you consider that you actually never terminate. So there are no states where you have to worry about what q is. So this is sort of vacuously true, and that's essentially what the proof has to do as well. Okay. There's a bit of work in the proof to establish, basically you have to show that p is an invariant of this loop. So every time you go around here, p is still true, and that's easy to show because the body is just skipped, so nothing happens basically. Okay, so yeah, the last part is just a mention of the fact that this sort of logic that we're talking about here is only part of the story, because it can only talk about terminating commands. Right? We can't sort of as easily reason about total correctness, which is also non-termination is sort of part of the, well, total is that everybody terminates, right? Whereas this is partial correctness, so it's allowing the possibility that some programs might not terminate. So you get these sorts of rules where you get a triple holding, even though you might not feel that that's terribly sensible. So partial correctness is what we're going to focus on here, and we're not going to force total correctness. Okay, so that brings us to the end of the lecture. So we've seen basically a way of structuring reasoning about program verification based on assertions, and this notion of the Hall triples, which lets you sort of relate assertions to each other based on the effect of various commands in the language. And we've seen a bunch of rules that let us sort of build up proofs of, correctness for large programs from smaller pieces in a compositional style. Okay, stop there, and I'll talk to you next time.